this would be P equals 0.5. This would be that she's doing better than just guessing, so P would be bigger than 0.5. And these two explanations are what we call our hypotheses. Now, a hypothesis, we basically use two different types of hypotheses. We have one that we use H with a subscript of 0, okay? This one we call our null hypothesis. The other one we're going to call HA, our alternative hypothesis. Now, you guys, when we did those probabilities, when we looked at that chart, or when we created that dot plot that we used to kind of help answer our question, did we assume she could smell Parkinson's or that she could not smell Parkinson's? What was true for you guys? You could smell Parkinson's on the cards or you couldn't? That you couldn't. Is everybody with me? So in reality, the way we came to our conclusion is that we assumed she was just guessing. Is everybody with me?
Yeah.
Okay. So the logic of one of these, what we call hypothesis or significance tests, is going to start like this. We're going to assume that null hypothesis is true. We assume she was just guessing that she had 50-50 shot. Yeah.
It doesn't have any actual weight, but like, why do we call it null versus alternative?
So null. So historically, it's called the null hypothesis, and the reason we use a subscript of 0 is the null hypothesis is an empty, boring hypothesis. It's the one that we don't want to conclude, essentially. Okay? So saying she's just guessing and got lucky is like, okay, it's empty. Our conclusion would be empty, null being empty. Okay? And so the whole premise of what we're going to do is if the sample is unlikely, we reject the null. And that's what happened, right? We said, hey, could she have guessed 11 out of 12 right by chance? And you guys were convinced because the sample was unlikely. So we said, hey, she wasn't just lucky. She can smell Parkinson's. So because of that unlikeliness of what actually happened, our assumption is a bad assumption. We're allowed to reject it. So we reject the empty one and conclude the alternative. So, the basic premise of what we're going to do is that exactly this, where we write a hypothesis, we decide could our sample have occurred with that hypothesis, and if so, we can't conclude anything, and if not, we reject the null and conclude the alternative. I'm going to take you through some examples. Okay, so before we can move on, we got to go ahead and decide what are our shape, center, and spread. So let's go ahead and this time we're going to do a slightly different value for p hat. Okay, so the first thing I want to point out is we are now assuming p is equal to 0.5, and I'm going to go ahead and say she had 20 t-shirts. So we're shifting into more examples, basically. Okay, so let's say they sent her 8 more t-shirts and she got 7 out of those 8 correct. So total, she has now gotten 18 out of 20 t-shirts correct. Is everybody with me? So if P is equal to 0.5, can we figure out what those P hats would look like? All right, so let's start with the shape. We would do 20 times 0.5 and 20 times 1 minus 0.5. Which is 10 and 10. And so surprising that that worked out just perfectly for those P hats to be normal.
I wonder how.
That's bizarre. Yeah. Okay. What is the center of those P hats going to be if the null hypothesis is true? 0.5. And the standard deviation would be 0.5 times 1 minus 0.5 all over 20.
What are we getting, y'all?
0.111.
Or 0.1118.
So we'll call it 0.112. All right, now, the next thing we're going to do is create something called a test statistic. It is actually going to feel incredibly familiar because we have already done them this year. Okay, our test statistic is going to be Z. Now, the test statistic is calculated by doing what actually happened minus what would be expected divided by the standard deviation. So if I wanted to find the z-score for this particular sample, well, our p-hat for this sample is 18 out of 20, which is equal to 0.9. Okay, so our z statistic is going to be that 0.9, what actually happened, minus what should have happened, which is going to be your mean, because that's what our sample should be, divided by the standard deviation, which is 0.112. What are we getting? I'd imagine 3.57. All right. Now, the next thing we're going to calculate is something called a p-value. And the p-value is a probability. It's the probability of getting the actual sample. You're going to calculate it using the distribution of z-scores, which have a mean of 0 and a standard deviation of 1. The number one mistake you guys will make is you won't use the mean of 0 and the standard deviation of 1. Okay? You need to. All right. And then you're going to apply the z-score that you just found of your test statistic and shade to the right. So your p-value is whatever you get from normal CDF. Let's see. All right, you guys. What this means is if she was just guessing, the probability she could get 18 out of 20 right is 2/10,000ths. Are you guys with me that it is very unlikely for this to get 18 out of 20 if the null hypothesis that 0.5 is true. Yeah.
In the normal CDF, would you put the lower as the 3.57?
Yes. And then the upper is some big number. And then for the mean,
It's the same number, it just shows up like this on the calculator.
you do 0 and 1.
I just forgot what you said. That OBS, when you said that.
The observed. It's the z-score is how does what actually happened compared to what should have happened if that null hypothesis is true.
I got 1.7 followed by a bunch of numbers, then E -4.
Yeah, that's essentially this. Okay? Because this is, keep in mind that 1.7, you probably got 1.78496 and maybe even a few more. What that E -4 means is times 10 to the -4th. I don't know why the keyboard keeps popping up. Okay? And that times 10 to the -4th, that would just mean that you move your decimal point 4 places to the left.
Yeah, but why is it like that? Because mine's also like that.
Your calculator will use scientific notation for anything that has more than 3 zeros or 4 zeros.
So do we just take like the
So,
thing at the end and
I-
just add zeros to the front, basically?
You have to add one less because it tells you how many places you're moving your decimal point. So the first one you move it.
Okay, so
Do you get what I'm saying?
I just add 3 zeros.
Or if you gave me this answer, I'd be fine with it. But what I want you guys to recognize is if you give me something times 10 to the -4th, that is really tiny. Like that's practically 0. That's an important idea. So I just can't have you look at that 1.78 and think that the probability is 1.78. To start with, probabilities can't be larger than 1. Do you guys get what I'm saying there? Okay? And I don't want you to miss that times 10 to the -4th. If you get something bigger than 1, you either need to put it in scientific notation or look for that scientific notation and move the decimal point. Is everybody good? Yeah.
There could be events that would be like more than guaranteed to happen, or is that just?
Now, you can have a percentage be higher. A percent can be bigger than 100%, but a probability cannot.
Gotcha.
So, for instance, if someone's salary is more than doubling, then they're getting more than a 200% raise, right? Like, it just depends. Cool?
Yeah.
Okay. All right, so the last thing we'll need to do is make our conclusion. I don't know why the camera keeps popping up. Okay. So here's what happened, you guys. Because our actual sample is so unlikely when H0 is true, we can reject. H0. So here's what I want you guys to think. Remember how we said we have two kind of hypotheses of what's going on here, right? There's two ways we could explain Joy not getting the 10 out of 20, right? One way we explain it is that she's just lucky. That was our null hypothesis. And the other is that she's doing better. That's our alternative hypothesis. And so what we just did is we said, what's the likelihood she could have gotten that just by chance alone and then she was just lucky? The answer to that is 0.00017. Super unlikely if that null hypothesis is true. So guess what we get to do? reject the null. And if I cross out that hypothesis, how many hypotheses do I have left? One. That is
Alternative.
the alternative hypothesis. She's doing better than just guessing. Griffin, did you have a question, bud?
I was wondering what the HO meant, but then I figured out that it meant null hypothesis.
Right on. Okay. Let's call this. So, I want to take you through a couple of examples of what I would expect you guys to be able to do, because tomorrow, believe it or not, you're doing a graded assignment over this topic. So I wanted to take you through a couple examples of how that graded assignment's going to look. Okay, so here we go. Mr. Richards claims he's a 70% free throw shooter. And you know how I feel about Mr. Richards. He's got a big mouth and he likes to hype himself up a little bit more than he deserves, if you know what I'm saying. Do you think he heard me just now? No, he didn't actually claim it. Do you think he heard me say that he's got a big mouth and he hypes himself? Well, hold on, let's try this again. You guys know how I feel about Mr. Richards. He's got a big mouth and tries to hype himself up a lot. We're doing is Mr. Richards a 70% free throw shooter example?
Very good.
I like to make fun of Mr. Richards whenever I can. In my defense,
Definitely like 25% from the line.
I bet he's better than 25% from the line, but I don't really know. I actually have never marched him down to the gym to make him shoot 50 free throws for us to figure this out. So here's the deal, y'all. We're going to go through this piece by piece on how to do this so that we're ready to go. What I ask you to do is to write your hypotheses. Okay. So you're going to have two, the null and the alternative. Now, in my opinion, the easiest way to do this is first think through what you want to be able to conclude at the end. So what I'm saying is that he is overstating his ability to shoot free throws. So does that mean I think the actual percentage for him is above 70% or below? Below. So my alternative hypothesis is that his shooting percentage is less than 70%. Your null hypothesis is going to be very similar with an equal sign. Because the whole idea is that we assume that null hypothesis to be true, so we want to have an equal sign so we know that we're assuming something. Everybody good? All right. So we then had him go shoot 50 free throws. So with n equals 50 and p equals 0.7, can we think through what the distribution of possible p hats would look like? Let's start with the shape. I would do 50 times 0.7 and 50 times 0.3. And I get 35 and 15. Those are greater than 10. So are you guys comfortable saying that the p hats will be approximately normal? All right. What about the center of my p hats? What's that going to be? 0.7. It's going to be whatever that p from the null hypothesis is. And the standard deviation of those p hats would be the square root of 0.7 times 0.3 over 50. I have no idea what that is, guys. Can somebody help me out? 0.069, thank you. Cool. All right.
It's 6.5.
Why'd you lie to me? Okay. Everybody good? All right. My regular old boring statistic is going to be the p hat of our sample, which is 32 out of 50, which 0.64. Okay. And my test statistic is going to be that z statistic. You're going to take the sample value minus the null hypothesis divided by the standard deviation.
Negative 0.92.
That's what I got.
Guys, why was it negative?
Because the top was negative.
But why was the top negative? Well, that's technically no. The top is negative because p hat is smaller than what we think would happen. But it makes sense that it's negative. Our sample supports that the sample is less than, that he's overstating his abilities, that his actual proportion is less than 0.7. So our sample also suggests less than, is essentially, when we get a negative value there, that suggests that less than is the right one. Okay. The next thing we're going to do is calculate the p-value. That's when we draw those pictures of those z-scores. Mean of 0, standard deviation of 1, and then negative 0.92 would be to the left of 0.92. So when our alternative hypothesis is less than, we shade to the left, whereas the one on the previous page, our alternative hypothesis was greater than, so we shaded to the right. And I don't know what the answer is. What are we getting? I would imagine it's roughly 0.2?
0.18.
0.182? Cool. All right, now.
No, there's not a 2 at the end. I was like, it basically rounds up to 2, but it's just 0.18.
Oh, got it. Okay.
I gotta stop telling you that.
You're stop talking to me.
Yeah, that's really what it is.
Okay, you guys. If Mr. Richardson is actually a 70% shooter, there's an 18% chance that he could get 64% on a 50-shot sample. Do you guys get what I'm saying here? Is that unlikely?
Pretty much. 18%
Is it unlikely enough that it makes you want to go over there and tell the big guy that he's lying about his abilities and that he's being too arrogant?
Yes.
You guys, even I don't want to go tell him that, and I didn't say just about anything to him.
Walter could
Yeah,
probably
we can
tell
send
him that.
Walter.
I volunteer you, Walter.
If this is an actual thing, I'll totally do it.
It's not real. The data's not real. Okay, so The basic premise is if our sample is unlikely, we reject the null hypothesis. So the question we really have is this 18%, the likelihood of our sample, is that low enough to make us assume that the null hypothesis is false? And the answer to that is, well, how low is low enough? Are you guys with me? Okay, so we have a specialized value. It's called a significance level. And we use alpha. You guys, that's the Greek A, alpha, to describe how unlikely something needs to be. For right now, I will either tell you what to use for alpha, or you can use 0.05 all the time. If I don't tell you, you use 0.05, okay? And on Friday, when we talk about type 1 and type 2 error, we'll talk about how do the people actually choose what alpha is. Okay, but that's a whole other thing that we got to talk about, okay? All right, so are you guys with me that in this case, our sample is larger than that sample, that percentage of our sample? And so what that means is we cannot reject the null hypothesis because my sample isn't unlikely enough to make me do so. All right, now, remember we started off with two hypotheses? I started out with two hypotheses, two explanations as to why he didn't shoot 70%, right? Either he is a 70% shooter and unlucky, or he's overstating his abilities. That's what these two would represent. And I cannot reject this first one. So I'm not crossing it out. So how many hypotheses do I still have? Two. So can I conclude anything if I have two explanations that could work?
No.
So if you don't reject the null hypothesis, we cannot conclude anything.
I should we take him down there and see.
He'd love it. He really would.
Is there nice block for you?
Is there basketball court at Cedar Point?
He has a basketball.
I have no idea if there's a basketball court.
Maybe one of those little mini games where it's like.
If there is,
Those are rigged.
can we bring Mr.
I'll beat him.
down and see?
We can try.
Why we
I have
test them on
80%.
it?
I have 80% free throw.
I don't believe you.
I have stats too because I'm in a rec league.
Okay.
But I've only taken 2 shots, so.
So I would say your sample size is not large enough for us to do anything with
Also,
that.
it would make sense.
from 2 shots.
Yeah, you can't get 80% from 2
I meant
shots.
2 times at the yeah, don't worry. So I have 4 shots.
So then how
You
does
still
that-
could.
You still couldn't get 80%.
You get 70.
All right, you guys.
10 times, 10 times, guys.
All right, next. Let's do another example real quick. A medical researcher says that 20% of all U.S. adults are smokers. You take a random sample of U.S. adults and of 200 U.S. adults and find that 29 say they are smokers. Okay, let's start with my hypotheses. And you guys, let's go ahead and calculate that p-hat real quick, that statistic. 29 out of 200. I don't know what that is.
That is 14.5%, but 0.1.
Flush good one, Cody.
All right, so our p-hat is 0.145. All right, and so are you guys with me that suggests less than 20% for the population?
Yeah.
Okay, so my alternative is going to be less than 0.145, meaning my no, I said less than 0.2, So my null is going to be equal to 0.2. Any questions on writing the hypotheses? The biggest mistake that tends to happen with students is they use p hat instead of the claim. All right, this is always going to start with the claim being 20%. Yes?
So is one always gonna be equal, then one will always be,
Greater than or less than? Yes.
okay, how do we decide if it's greater than or less than?
One of two ways. Like on this one, we decided because we're trying to say that he's overstating his abilities. This one, the sample suggests less than, so that's the direction we're going to go. Does that kind of make sense?
So could we take the p hat and since it's less than that? Okay.
Correct. Is everybody good? Next we do that normal condition, so I'm going to do 200 times 0.2 and 200 times 0.8. That would be 40 and 160, I think. So that normality's there. Woohoo! What's the mean of all those p hats going to be? 0.2. And the standard deviation of the p hats would be the square root of 0.2 times 0.8 over 200. I don't know, 2.3. .023 is my guess, but I'm not smart.
1.168.
0.028. Did you take the square root?
Yep. 2 times. I did 28 for some reason.
Okay. Alistair, can you tell me that one more time, please?
0.0282.
I'll leave it there. All right, that makes my z statistic. We're going to do the 0.145. Just a reminder, guys, that's p hat minus p over the standard deviation. That's how we're going to calculate this. So it's going to be 0.145 minus 0.2, all divided by 0.028.
Negative 1.9. 6.
Cool. All right. So to calculate that p-value, guys, this is when we compare with a distribution of 0 and 1. Here's negative 1.96, and since we have a less than, we're going to shade to the left. So what is the area left of negative 1.96?
Negative infinity? Or the area left?
What is the area? So the lower boundary is negative a gajillion. My upper boundary is going to be negative 1.96. My mean is going to be 0. My standard deviation is going to be 1. I'm assuming it's a little bit less than 5%. Am I close? Oh, a little bit less than 2.5%.
Yes. 0.0249.
So my p-value is 0.0249. So yeah, just a little bit less than 2.5%.
How do you know how to do that in your head?
Do you guys remember when we did the confidence intervals and we had the 95% confidence intervals? It was that number. But also, Alistair, I literally do this all day, every day at this time of the year.
I suppose.
So I have some pretty good gauges of this.
Does this get boring?
Nah.
for you?
I love this.
She likes really show enough. Clearly.
You guys, how does that compare? So this time I'm telling you to compare that to a different value for alpha, the 0.10. And how does this number compare to 0.1? It's less than. So now, what that's basically saying is our sample is unlikely enough that we can reject the null hypothesis. And you guys, if I reject the null hypothesis, how many hypotheses do I have left? One. And what does that hypothesis mean in context? Like, don't just tell me that P is less than 0.2.
Less than 20% of variance.
Cool? All right. So tomorrow you're going to be asked to do some of these. I will not be here.